So in this video, we're going to talk about type 1 errors, type 2 errors, and power, and what affects these, as well as how we can work out their numeric values. We're going to do all of this for hypothesis tests for one mean. And again, we're going to use this as a foundation for what is power, what is a type 2 error, what are the things that affect them, what are the concepts they're based on. What's most important as we go through this explanation is the concept of power and how it's calculated, not the actual calculation itself. Okay, we're going to run through the calculation so we can help understand the different things that affect power. But again, the most important thing is understanding the concept. Okay. Often we're going to work with estimates that are more complicated than a simple mean. And when doing these power calculations, we're usually going to work with software. So we're not going to be doing this stuff by hand. Plugging into formulas is not an important skill to gain. But the reason for doing this is so we can illuminate some of the concepts. So to do this, we're going to work through this simple example here. So we're going to suppose that there's some hypertensive population, and we know that their mean systolic blood pressure is 160, and their standard deviation is 36. Then they're given some drug that we think may lower blood pressure. We're going to give this drug to 25 people. We're going to test their blood pressure. We're going to measure their blood pressure. And we're going to see if we have evidence to believe that this drug is effective in lowering mean blood pressure. So we're going to work with the following null hypothesis. Start by assuming the drug doesn't work. An alternative that it does work, and now the mean is significantly less than 160. So when we work our way through this, we're going to do a one-sided hypothesis test. And the reason for this is just to simplify things. We only have to look at one tail of the distribution rather than two. And again, we're going to use Z, the standard normal, rather than the T distribution. Again, just to simplify things a little bit so we can focus on the concepts. So first, just a reminder what a type 1, type 2 error and what power are. And putting these in context, right? A type 1 error is where we reject the null. Right? We say that the drug is effective in lowering blood pressure, when in fact it's not. A type 2 error, we fail to reject the null. Right? We say we don't have evidence to believe the drug is effective in lowering blood pressure, when in fact the drug is effective. Okay, and the power, which is one of the most important ones, tells us what's the probability of rejecting the null if the alternative is true. Okay, so essentially, what's the probability of us concluding this drug is effective in lowering someone's blood pressure if in fact the drug is effective at lowering blood pressure? So, as noted previously, these here, type 2 error and power, we said that they depend on the alpha that we're using, the sample size, and the difference that we wish to detect. Okay, we're going to build up to all of these here. So first, let's think about what's needed in order to reject our null hypothesis. Right? You can see here the type 1 error as well as the power involve rejecting the null. Right? What's the probability of rejecting the null? Okay, so let's think about that. How do we reject the null hypothesis? So here we're doing a one-sided hypothesis test, and we're going to use an alpha of 5%. Okay, so essentially what we want to find there, and this is if the null hypothesis is true. This is looking at our test statistic. What value for the test statistic has 5% below it? Okay, and if we look that up in the Z table, we're going to find it's approximately negative 1.65. So any test statistic that's 1.65 or more standard errors below the mean is going to have a p-value less than 5%. Okay, so again, any test statistic less than negative 1.65 means we'll reject the null. Now, let's take this back on the scale of the sample mean. Okay. So, well, let's write that down first here. Any Z statistic, okay, or technically it should be T statistic, but we're using Z to simplify, less than negative 1.65 implies we're going to reject our null hypothesis. Okay. And we also know when we standardize, okay, when we calculate this test statistic, how far is our estimate from the hypothesized value in terms of a standard error? Okay, and subbing those in, right, our hypothesized mean is 160, and our standard error is 36 over square root of 25. Okay, and again, we're working here with the population standard deviation. If we had a sample, we just sum in the sample standard deviation. Right now, we're just assuming population's known, using Z rather than the t distribution to simplify things and focus on the concepts. But now we know we need Z less than negative 1.65, and we know that this is Z here. Sample mean minus 160 over 36 divided by square root of 25. Okay. So what we know is Z, the kind of critical point, is negative 1.65, and Z is also x bar minus 160 over 36 divided by square root of 25. Okay. And if you're to work this out, okay, solving for x bar, right, so bring this over to the other side, add 160 to the other side, x bar of 148.12. And so drawing that out here, any test statistic of negative 1.65 or less means we're going to reject our null hypothesis. On the scale of the sample mean, okay, again, this is if the null hypothesis is true, meaning if 160 is the true mean in the population, any sample mean of 148.12 or less means we're going to reject our null. Okay, and again, this is that same 5%. Then if we want, we can label these here. Anything less than negative 1.65 means we're going to reject the null hypothesis. Anything larger than that, we're going to fail to reject the null hypothesis. Okay, or again, thinking on the scale of the sample mean, right? Any sample mean of 148.12 or less, we're going to end up rejecting the null hypothesis. Any sample mean greater than 148.12, we're going to fail to reject the null hypothesis. Okay, so again, sometimes these get labeled as critical values. And this tells us how far does our estimate need to be from our hypothesized value before we can reject the null. Okay, so this is kind of the cutoff. Once we get a sample mean of 148.12 or less, okay, that's going to mean a p-value of 5% or less, okay, and help us reject our null hypothesis. Okay, so this is one of the parts that we need in order to work out power, okay, or type 2 errors. Right? We now have the threshold at which we're going to reject the null or fail to reject the null. Okay. All of this, though, was in the context of the null hypothesis being true. Okay. You'll notice, in order to work out the type 2 error rate, beta, okay, or the power, this is in the context of given the alternative is true. Okay, so let's start to talk about what do we mean by when the alternative hypothesis is true. So let's get to talking about working out beta, okay, or the type 2 error rate. So you'll notice in order to work this out, okay, the type 2 error or the power, these require the condition that the alternative hypothesis is true. Okay, they're supposing what's the probability of rejecting or not rejecting the null when the alternative is true. So what do we mean by that? Saying that the alternative is true is saying that we believe that the mean is less than 160. But what is it? Is it 159? Is it 150? Is it 140? Okay, so to work out the type 2 rate or the power, these depend on us specifying a value under the alternative hypothesis. Okay, so let's work out the power, okay, or the type 2 error rate. We'll start with that, type 2 error rate. Supposing that under the alternative, right, that the alternative is true, the mean is less than 160, and suppose that it's now 145. Okay, or in other words, we've got the mean of A minus mu naught, right, being negative 15, right, going from 160 down to 145, or a decrease of 15. Okay, so again, this is what we meant when we were talking about the difference we wish to detect. Okay, and again, we'll expand on that a little bit more. Let's draw out the diagram here. Right, this we just talked our way through, and this was under if the null hypothesis is true. So what if the alternative hypothesis is true? And let's suppose that under the alternative, the mean has decreased down to 145. Okay, so that's sitting right about here, 145. And again, this is the mean under the alternative hypothesis. And if we were to draw the sampling distribution here, look approximately like this. Now, looking at these here, let's highlight beta on this graph. Okay. If the alternative hypothesis is true, so maybe let's label that here. If the alternative hypothesis is true, okay, if the mean has decreased and it's decreased down to 145 now, what's the probability of failing to reject the null? Again, remember we determined this is our cutoff for rejecting or failing to reject. So if the mean is now 145, what's the probability of failing to reject the null? Okay, that's this area up here. Right. Again, hopefully you can see what I've highlighted there is telling us what's the probability of failing to reject the null if the alternative is true. Right? If the mean is really 145, how likely are we to not reject the null? Okay. And this, again, we label beta. And I'll just, I don't want to overcrowd the graph too much, but I'll just point the arrow on this side. This side here is the power. Right? The probability of rejecting the null, right? Any estimate on this side of this threshold, we're going to reject. Right? The probability of rejecting the null if the alternative is true. Okay, so let's go and quickly work this out numerically. So as noted, I'm going to start by working out beta, the type 2 error rate. What's the probability of failing to reject the null if the alternative is true? Right? We can write this out as what's the probability of getting a sample mean greater than 148.12 given that the true mean is 145. Okay. Or if we want to sketch it out here, it's isolating this purple curve here. If the mean really is 145, how likely are we to get an estimate of 148.12 or more? You'd work this out in the usual way. Z beta, right, we're going to standardize it. And we're looking at how far is the 148.12 from 145 over 36 divided by square root of 25. That comes out to 0.43. And again, if you look up in the Z table, so look up the Z table or use a software, the area above 0.43 is going to come out to be roughly 0.333 or 33.3%. Okay, so in other words, if the alternative is true, if the drug does work and it decreases blood pressure to about 145 on average, there's a 33% chance that we end up failing to reject the null. Okay, we're looking at it in the context of power. What's the probability of rejecting the null when the alternative is true and we should reject the null? So you can notice the power is 1 minus beta, 66.7%. So then if the drug is effective, if it decreases blood pressure on average by 15 units, there's about a 67% chance that our test concludes this drug is effective at lowering blood pressure. Okay, and again, the actual calculations itself aren't really the important part. The concepts displayed in them are what are most important. Let's talk a little bit about the three things that affect the type 2 error rate, or let's talk in the context of power. Okay, so let's talk about the three things that affect power. First thing is alpha. And let's think about what happens if we increase alpha. Okay, so let's look at this diagram and try and visualize if we want to move this alpha, say from 5% to 10%. What's that going to mean? That's going to mean shifting the rejection threshold a little bit this way. right, to get 10%, say, a larger value of alpha below. If we shift this rejection line over, what's going to happen? You can see beta, the type 2 error rate, is going to decrease, or the power is going to increase. Right? Hopefully you could see that visual. Increasing alpha decreases beta, okay, or increases the power. And we noted this earlier, the trade-off between type 1 and type 2 error rates. If you want to have more false positives, you're going to have fewer false negatives. You want fewer false positives, more false negatives. Okay. Let's think about what happens to the sample size. If we increase the sample size, the way we can try and visualize it here, increasing this sample size is going to decrease the whole standard error. Okay. So what it's going to do is take these sampling distributions and narrow them in a bit. So again, we can see what's going to happen. Let's just visualize it happening to one of them. I think that's a bit easier to think of. Let's picture the blue one here. Okay. With a larger sample size, the standard error is going to become smaller. This curve is going to tighten up a bit. Right? This blue area is still going to be 5%, holding alpha constant. So what's going to happen? As we shift this over, right, our rejection line is going to shift over. We're going to have a smaller beta or a higher power. Okay, again, if it helps, maybe think of it just isolating the purple curve. Right? Think about what happens as the sample size goes up, standard error goes down. This curve narrows in. Right? This tail starts to drag over here. The beta side is going to get smaller. The power side is going to get larger. So increasing sample size decreases the type 2 error rate, or it increases the power. Okay. And finally, let's think about that difference we wish to detect. First, let's think about what happens if we increase that. Okay, so rather than looking for an effect of decreasing blood pressure by 15 units on average, let's suppose we want to look for an effective size 25. Okay. This here is the difference to detect. Right? The difference between the mean under the null and the alternative. If we look for a bigger difference, right, what that's doing is taking this purple distribution here, right, the distribution under the alternative, and shifting it over this way. Again, what's going to happen is it shifts over this way. Right? This threshold stays the same. As the purple curve shifts to this side, the beta area is going to get smaller, power is going to get larger. And so again, this is going to decrease the type 2 error rate or increase power. Okay. And to think of this conceptually, if the drug, suppose, has a really big effect, okay, the effect is really large, it's really good at lowering blood pressure, we're not going to need to look at too many people to notice this. Let's suppose on the other side, we're looking for a really small effect. Let's suppose that this drug does work, but it only lowers blood pressure by 2 or 3 units on average. We're going to have a hard time finding that difference, or we're going to need a really large sample size in order to pick up on that small effect. So these are the things that affect the type 2 error rate or affect the power. Okay, you'll notice that the easiest one for us to work with is the sample size. We can control our sample size, and we can use that to control our power. Okay, so if we want to have a higher power, and again, a higher probability of rejecting the null and saying the drug works when in fact the drug works, we can do that by increasing our sample size and increasing the power. Doing these sample size calculations is something we should do ahead of time rather than collect data, run analysis, calculate our power, and find out that it's too low. Quite often we want power somewhere in the range of 80 to 95% is usually the ideal sweet spot. And again, just a reminder, everything we ran through here is not to focus on the calculations. Those are of secondary importance. It's to understand the concept of what is power, what affects it, how can we control it. Okay, when we get to looking at more complicated estimates, all these same concepts are going to hold, but rather than looking at a mean, we might look at difference in means or odds ratios or rate ratios or correlations or even more advanced estimates, but the underlying concept always holds.
Hope you guys liked the video. Subscribe to our channel, like our videos. Stick around, guys, because we got lots more. Statistics is hard to say, Poopalu. And I'll sign up, Poopalu.